Today we are going to see about economic load dispatch by using the gradient method. Already we have seen the algorithm in the previous class. Now we are going to solve a problem so that you can better understand how the complexity is being reduced by choosing this kind of method, that is gradient method. So take on this problem. While solving the problem itself, we can just compare with the other algorithm also, and how much time taken. Okay, how much time taken by you, so that we can understand this problem very easily. Okay, take down this problem. Determine the economic generation schedule of determine the economic generation schedule of three generating units in a power system to meet the system demand of 800 megawatt. Okay, so here the demand, how it is given is demand is given as 800 megawatt using the gradient method. Using gradient method. So take down this fuel cost function as same like previous fuel cost function. So the three fuel cost function is being given. That is F1 of P1 is equal to 561 plus 7.92 P1 plus 0.001562 P1 square. Next, F2 of P2 is equal to 310 plus 7.85 P2 plus 0.00194 P2 square. Next, third generating units, fuel cost function of third generating unit. F3 of P3 is equal to 78 plus 7.97 P3 plus 0.00482 P3 square. So this is the problem is being given. So this fuel cost function is being given. So in the problem, the demand also given, but the thing is that you need to solve this problem using this gradient method. Already we have seen. So once again, we'll refresh the gradient method so that the solving the problem also will be very, very easy. So this algorithm already we have seen. Just for refreshing, what is the step one? We need to select the starting values for power generation. That is for first generating unit, third generating units, up to nth generating units. So whatever the generating units that is given in the problem, whether it might be 2 generating units or 3 generating units or 10 generating units or 100 generating units. So first we need to select the starting values for this these values, such that it should meet the demand. So always you have to remember that. So whatever the values that is being considered, that should meet out the power demand. Okay, so don't simply assume the values, some other values, then your problem might be goes wrong. Next step, what we need to do is what is the second step? We need to compute lambda I naught. So what is the formula for lambda I naught? Lambda I naught is equal to dFi divided by dPi by substituting the values of Pi, that is PGI. By substituting the values of PGI, we need to find out the lambda naught for each generating units using this equation. So this is the equation. So what we need to do is we need to substitute the each values of P1, PG1, PG2, PG3, so up to PGN. Okay, so we need to substitute these values and we need to find out this lambda I naught. So what is the step number 3? Step number 3 is compute initial average incremental fuel cost. So what is the initial average? So initial average is lambda I. Okay, so lambda. So lambda is equal to 1 divided by n. Summation I is equal to 1 to n lambda I naught. So already we have calculated, say for example, 3 generating units means we have calculated the lambda I naught for 3 generating units. That is lambda 1 naught, lambda 2 naught, lambda 3 naught, like that we have calculated for 3 generating units. So whatever the values we have calculated, we have to take the average. How to take the average? How many generating units are there? That you need to see. Say for example, 3 generating units are there. So you need to divide to take the average. So what is the next step? Step number 4. Step number 4 is to compute the gradient by using this formula. So if you know this formula directly, you can take, or otherwise no need. Calculate once again the Lagrange's function and frame this, that is gradient of L. Okay, so you know what is the objective function of the economic load dispatch? To minimize the total fuel cost, that is to minimize this fuel cost, that is FI of PL. So how to frame the Lagrange's function? Lagrange's function is equal to objective function plus some constant into constraints. So what is the objective function? This is the objective function, that is minimize the total fuel cost plus what is the constant? Lambda. What is the constraint over here? This is the power balance constraint, that is the generation that equals the demand. So the PD, that is PD minus PI. So already we have framed this equation. So PD minus PI. So we are neglecting this demand. We are considering this demand might be very larger. So we are neglecting the demand. And what we are doing is we are differentiating. We are differentiating this, that is Lagrange's function with respect to that power generating units, that is dou L divided by dou P1. So gradient of L is nothing but dou L divided by dou P1, dou L divided by dou P2, up to dou L divided by dou Pn, up to dou L divided by dou Pn. Okay, so here if you see what is dou L divided by dou P1, dou L divided by dou P1. So if you differentiate with respect to P1, so what is the first? It will come. So it is dF1 divided by dP1. Okay, so here plus lambda, so this term, that is PD term, becomes 0. Okay, becomes 0 over here. So what we need to do? So here 0 minus 1. So while differentiating P1, if you are differentiating P1, this term will become 1. Okay, so this term will become minus lambda. So similarly for all generating units. So if you calculate, so finally it will be like dF1 divided by dP1 minus lambda. Okay, so what is the differentiation of second? So dou L divided by dou P2. Dou L divided by dou P2 is what is here? So here you need to differentiate this term with respect to P2, because you are calculating for second generating units. So with respect to P2 means this will come as it is, that is dF2 divided by dP2 plus lambda. Here also same will come. So here 0 minus 1. So it is minus 1. So here dF2 divided by dP2 minus 1. So up to PD minus PA. So why we are doing this PD minus PA in the sense? So we can clearly know whether the demand, whatever the generation we have considered, it is satisfying the demand or not. Otherwise, say for example, unknowingly you have considered some values. So here, if you unknowingly consider some values, here it will come some other values. In the problem, what is the demand is being given? So 800. So 800 means you can consider some values, some 400, some 200, like that. You can consider some values. So whatever the values, the power generating values you have considered here, okay. So it should satisfy the demand. If it is satisfied, then it will come as 0. That is PD minus. So whatever the values here you have considered, that is come as say for example 800 minus 800, it will come as 0. So next we have to select the scaling factor alpha for convergence. So as I already said, convergence, if you are not selecting the scaling factor, then the same algorithm, if you are programmed with any software, with some programming language, this algorithm will run for n times. Okay, it will not come to a convergence. There should be some convergence point. Okay, whether that program has to stop up to that particular limit. Okay, if say for example, if the considered amount of output is reached, okay, you're taking power demand as 800 megawatts something. So if the power demand is reached, then you have to stop the problem. Or the condition, whatever the condition you will be given, some scaling factor, some convergence factor you need to give. So that is this alpha. Next, what is the step number 6? Step number 6 is compute the new values of power generation using this equation, that is x dash is equal to x naught minus del L into alpha. So now we are going to the problem. So here this is the problem is being given. We have taken the fuel cost function F1, F2, F3. So now what is the first step? First step, we need to find out we need to assume the initial values of power generating units and also power generating units. So here, what are the initial values? What is the demand is being given? 800 megawatt. So this you can consider anything. So for simplification, I have considered like 300, 200, 300. You can consider any of the values, but it should reach the demand. So as I said, in the real world, how in the real world, how you have to choose this value in the sense based on the installed capacity of the plant. Installed capacity, how it will be, like as I said, like a 500 megawatt, 1000 megawatt, 1500 megawatt. If you take like thermal generating units, it might be this value. So if you consider some hydro units, like a minimum like a 100 megawatt, 200, 500, like that, it will be there. So mini hydro power plant means some 20 megawatt, 15 megawatt, 10 megawatt, 30 megawatt, like that. So whatever the installed capacity, based on the installed capacity of the plant, you should choose this value. So in real world problem, you can easily know this value, no need of considering. But for in the problem, we don't know the installed capacity. So for simplification, we are considering like 300, 200, 300. You can also take any other values instead of 300, 200. You can also take like 400, then 200, 200 also you can take. Then 500, 200, 100, like that. But it should meet out the demand. That you should very, very careful. So I have taken in this problem like P1 naught, that is initial values. P1 naught is equal to 300 megawatt. P2 naught is equal to 200 megawatt. Then P3 naught is equal to 300 megawatt. So this is the first step. That is the consider the initial values of the power generating units that we consider. So it is also meeting out the demand. So what is the next step? Step number 2. Step number 2 is to find out the lambda naught. So what is the formula for lambda I naught? So lambda I naught is equal to dFi divided by dPi by substituting Pi. So if you take if you substitute I is equal to 1, that is summation. Summation I is equal to 1 to n. So first you are substituting I is equal to 1 for first generating unit. So if you take here, that is dFi divided by dP1 by taking P1 as 300 megawatts. So here I made a mistake. So here dF1 divided by dP1 by taking P1 as 300 megawatt. So what you need to do is you need to differentiate this equation, that is first fuel cost with respect to P1, and we have to substitute P1 as 300 megawatt in that. So first you differentiate. First thing you differentiate. If you differentiate, you will get answer like 0.003124 P1 plus 7.92. Okay, so here you need to substitute. Here you need to substitute P1 is equal to 300 megawatt over here. So while substituting P1 is equal to 300 megawatt, so what is the answer you are getting? Answer you are getting as 8.856. 8.856. That is lambda 1 naught. So lambda 1 naught. So here you substitute, and so after decimal, as I said, after decimal you have to take 4 digits. Don't round it off. After decimal you have to take 4 digits. So by taking this value, so you can take like dF1 divided by dP1 is equal to, like by substituting 300 megawatt, you will be finding the answer as lambda 1 naught is equal to 8.856. Next, similarly, you need to find out dF2 divided by dP2 by substituting. Okay, so whatever the answer we have, whatever the value we have considered, that is P2 naught as 200 megawatt. By substituting P2 naught as 200 megawatt, you need to find out lambda 2 naught. So by substituting P2 as 200 megawatt, So here after substituting, you'll get 8.626. Okay, like we are getting 8.626 lambda 2 naught. Next, similarly, so what we need to do is we need to differentiate the fuel cost function 3. Okay, with respect to P3. So what we are doing is we are differentiating. So we are getting 0.00964 P3 plus 7.97. So here what we are doing is we are substituting P3 as 300 megawatt as we consider. So here as we consider, so like after taking P3 as 300 megawatt while substituting, I think you are getting the same values. I think so. 10.862 something we are getting. So I think same value also you can get. So I rounded up to 3 digits. You don't round off. Why? Because for getting the accurate answer, you don't round off. After decimal, 4 digits. So you are getting lambda. Now we are getting lambda 1 naught, lambda 2 naught, and lambda 3 naught. Now what we need to do is we need to take an average. Next step. What is the next step? We need to take the average. We need to take the average of this incremental cost. That is lambda is equal to 1 divided by n, summation I is equal to 1 to n, lambda I naught. So whatever the lambda I naught, that is lambda 1 naught, lambda 2 naught, lambda 3 naught. So whatever the values we got, we need to substitute over here, divided by n. So n is nothing but number of generating units, or how many generating units you are taken into account. So that is nothing but in this problem it is 3. So we are taking this 3. Okay, average. So here like 8.856 plus 8.626 plus 10.826. So these are the 3 values we have calculated previously. That is lambda 1 naught, lambda 2 naught, and lambda 3 naught. So we need to take average. The average if you take like it is coming like 9.4434 like that, it is coming as the average. Okay, this is the step number 3. Next, compute the next. What is the step number 4? Compute the gradient. How to compute the gradient? Gradient del L. Okay, del L is equal to df1 divided by dp1 minus lambda, then df2 divided by dp2 minus lambda, then dft divided by dp3 minus lambda. Okay, so here you can also add a PD minus PI, that is power balance equation also. You can add over in this matrix itself. In one matrix itself, you can add. So here it will be coming as 0. Why? Because we consider the values within the that is whatever the demand is being given. If it is coming like a minus values, or it is coming like some other values, then the whatever the considered value is wrong. So for better understanding, that value also you can add over in this matrix. Okay, so after this, suppose say for example you forgot this, how to derive that is del L. No problem, just frame the Lagrange's equation. Then from the Lagrange's equation you can easily calculate dou L divided by dou PI, that is dou Li divided by dou PI. So whatever the that Lagrange's function we frame now, that we need to differentiate with respect to P1, P2, and P3, and you can find out the answer. So if you take this, then df1 divided by dp1 minus lambda it will come. Similarly, df2 divided by dp2 minus lambda. So here also same, df3 divided by dp3 minus lambda. So we have calculated already this value, that is df1 divided by dp1 by substituting some values. That is, what is the value here? df1 divided by dp1 by substituting 300 megawatts. We have calculated, that is 8.856. Or you can instead of df1 divided by dp1, we can also take lambda 1 naught minus lambda. Okay, so for you'll get like confusion, so that only I have taken this. So the lambda 1 naught minus lambda also you can take. Okay, sometimes if you take like this, instead of substituting lambda 1 naught, you will substitute 9.44384. then you'll substitute this value for that value, then the answer will come in sometimes a negative, sometimes you need to round up, something like that, some careless mistakes you will do. So better you can take like this, that is df1 divided by dp1 itself for a easy understanding. Okay, so you need to substitute the values. So what is the value we already calculated? That is 8.856 for first generating unit. So minus the lambda. So whatever the value you got. Okay, you take full values. I rounded off here. You don't round off. And repeatedly saying this. Okay, so you have to substitute this value. Similarly, for all three generating units, that is df2 divided by dp2, then df3 divided by dp3. So minus this lambda. This lambda is same. There is 9.4434, like that. You need to substitute. So if you substitute, you are getting the value like minus 0.584 minus 0.814, then 1.42. Like that, some the values you are getting as this del L, that is gradient of it. So del L, you are getting this values. Okay, so what is the next step? Step number 5. Step number 5 is you need to assume the scaling factor. Okay, scaling factor alpha for convergence. So here in this problem, I'm taking it as 100 as a scaling factor. Okay, in this problem, you can also choose any other values between 0 to 100 or 1000 also you can take. So you choose this value and try to refine your answer. Okay, if you choose at 10 also some values, some answer you will get. If you choose some 0.1 also, some values you will get. If you choose 1000 also, some other values will get. While doing programming with the MATLAB, same algorithm, if you program with the MATLAB or if you program with some other programming languages like C programming, Python programming. So whatever the platform it is convenient to you, while doing the program, then if you change this alpha value and C now, you'll get better convergence. While seeing the programming aspects, I will try to change this alpha value, and here also in while do solving also you can consider some other values and you can see. But in programming it is very easy. In programming, simply like that, you can change instead of 100 you can change to 0.1, 0.01, then 1 or 10. Like that, some other values you keep and see how the convergence, how fast the convergence you're getting, like that also. So in this problem, I am taking this alpha as 100. Next, what is the step number 6? So step number 6 is x dash is equal to x naught minus del L into alpha. So x naught is nothing but initial values of all the power generation, whatever we consider. So whatever the values we consider, like first values, initial values, that is 300, 200 and 300. Next, 9.484, that this lambda value, that is the lambda value we calculated now, that value also we are adding over here. Okay, as per our convenience, we are adding over here. Why? Because this is as per the algorithm. Why we are projecting all the values here itself. So for this value of lambda, we are getting this answer. Say for example, we are getting the final answer as some 299 or some 199, then some 302, something like that. You say for example you are getting now. For this value of lambda, so lambda value also we are projecting over in this matrix. So for this value of lambda, what is the answer? Like that we can easily understand. And here we are adding power demand also. That is power balance constraint also, that is PD minus PA. So this value also, if we are projecting, you can easily we can know like the demand is get satisfied for this particular problem. So what is the initial values we consider? That is 300, 200, 300, and the lambda value, whatever the value we calculated, that is 9.4484. So whatever the value you are getting, that you add over here, because someone may consider this values like so 400, 200, and some 200, like that also. Someone might be considered. So for you, you will be getting the different answer over here. So whatever the value you are getting, that also you can add over here. Next, del L. Del L value already we have calculated. Gradient of L. What is the gradient of L? Here, this matrix we already calculated. That is minus 0.584, minus 0.814, 1.42. Like that, the values we already calculated. The same values, what we are doing is we are substituting over here. And alpha value also you are taking. The alpha value I have considered here, it as 100. You can consider like whatever the values you want, like 1,000, 0.1, 10, 1, like that. That convergence value also, scaling factor also you can consider and see how the answer is getting varied. So in this problem, I have taken as I have considered the alpha value is 100. Okay, now I am substituting this alpha value 100 over here. Next time, further I am going for further simplification. So after further simplification, I am getting the answer like this. Then 282.24, then 158.64 megawatt. This all three in megawatt. This is the lambda value. Okay, this is the lambda value, lambda value. So from this, we can easily like in one matrix itself. In one matrix itself, we are having P1, P2, P3, and also for this value of lambda, you are getting this thing. Like that, we easily we can find out the answer over here. That is this x dash. That is the initial value. Initial value. So x dash is nothing but x naught minus del L into alpha. So what is the x dash, x naught? That is the initial values. So del L already we have seen. Already we have seen in the problem. What is the del L here? Yeah. So del L is nothing but, yeah. So dou L divided by dou P1, dou L up to dou L divided by dou P1 again. And also we are taking dou L divided by dou lambda. So that value also we are taking. So that is nothing but PD minus PA. PD minus PA. So whatever the values, and also we are finding out the initial values. Initial for this new values of the power generation. So new values of the power generation, we are getting like x dash equal to x naught minus del L into alpha. So the same value we are getting over here. So for any this is the only the example problem. Say for example, in your exam, they may tell like they have given one problem with this some answer without they are telling you to solve using the gradient method. So you can follow this algorithm. You can follow this algorithm. You can assume some certain values. In some other problems, this assumed values also priorly they will be given. Okay, or in some other problem, what they will do is they will give some minimum and maximum operating constraint. You have to choose the values between that constraints alone. That also sometimes because the installed capacity, based on the installed capacity, they can know from starting from 400 megawatt to 500 megawatt or 500 megawatt to 1000 megawatt. Like that, some values that they might be given. So within that values, you have to choose. In some other problems, directly assume, say for example, installed capacity of the particular plant might be of 300, 200, 300 megawatt. Like that also might be given. And in some other problem, like for convergence value, take the convergence value as 0.1 or 0.01. Like that also convergence value might be given in the problem. So with that convergence value, you can easily solve this particular problem. And you can, so whatever the value given in the problem, you can easily solve. Or otherwise, you can assume the certain values and you can further proceed this problem. problem, you might be getting the answer like this. So how this is only, I think, if you neglect the step number 5 and the step number 1, I think you'll be getting only 4 steps. Within 4 steps, you are getting the answer. Okay, so previously we need to differentiate and we need to equate it to lambda. Then again, you need to find out lambda. From that lambda, you need to find out P1, P2, P3. So many calculation all there. So to avoid that calculation time consumption, so this one of the algorithms. This is not only algorithm. This is not only algorithm. We have seen many algorithms, lambda iteration method algorithm and all. So this is a gradient method. So some other methods also, the base point method and participation factor method. Like that, many methods are there. So like some important methods we are going to see, and further we are going to proceed. So why I am taking more problems on this particular thing is in the sense, see, whatever the problem in the exam they will be given, so you need to solve. Why? Because in this particular first unit, if you take this particular first unit, so mostly first 2 units you will get only problems. Sometimes maybe theory, but 99% you will get problems. So whatever the problems might be given, so you will not suffer in that time. Okay, sometimes they might be given some alpha value. So simply like that, they might be not mentioning any method. Say for example, you need to solve using gradient. So by seeing the alpha value, simply like that, you can solve using this gradient method, like scaling factors being given, or sometimes initial values of for the power generation is being given, and alpha value. Sometimes like that, if you given directly, you can go for this, choosing this method, and you can proceed the problem, and you can find out the answer easily. Like only 4 steps. 4 steps, within the 4 steps, you can simply get the answer, so that you can solve this problem very easily.